Welcome to a video on common base amplifier design. Right, so the common base is one of those amplifiers that is very popular in high frequency applications because it has a very high bandwidth and a very small input impedance, which is typically required when dealing with antennas. So we're going to look at component purposes and functions, influences, design parameters and specifications that you will encounter when dealing with common base. There's not a lot. And then some design examples and simulations. So I've picked out two designs. It is not very complicated. People are afraid of common base, but it's actually a really simple amplifier to design. So the purpose of each component is quite straightforward with a common base. As usual, if you know what the purpose of a component is, it will help you with selecting or tweaking a value later on. So the collector resistor together with the VCE is responsible for the output swing and the gain of amplifier. Now the common base typically has a very large voltage gain, but it's not a nice voltage amplifier because it has a very small input impedance, looking backwards at R pi and that becoming small RE, which is a very small impedance, but makes matching with other circuits um, for low impedances quite easy. Um, so continuing on, the emitter resistor is responsible for the bias point. So this is to pin the bias to the load, and then these two resistors or single resistor depending on the bias configuration is just to provide either the voltage required here or a path for the current into the BJT. Right, C1 is a bypass capacitor, and in the small signal model these two resistors will disappear entirely, so its only purpose is biasing the transistor. Capacitor 2 and 3 is again for decoupling. Any DC from the input side, any DC, this is some kind of other system. And it's also to remove DC going into the output. And then just again, RS and RL is our loads, our input load and our output load. So there is mainly three components to design in this amplifier. So the typical specifications that you will encounter is a specific loaded gain. So this is when we have R load prime, which is just R load in parallel with RC. This is also typical for common emitter amplifiers, and you will deal with this on the same way. I have not done this with a common emitter amplifier examples because there is more use for this or more place to demonstrate this during common base. There was a lot more to demonstrate during the common emitter, and I feel this is typically quite trivial. Okay, so typically designed for a specific load, and from that you will get your RC, and R load prime is just when you have a specific loaded gain. So this is not the maximum gain of amplifier, this is the loaded gain of amplifier. In general, try to design ICRC equals to VCE. Then you can design for matched impedance or power transfer to the load or to the source, and it will be more common for Z in and RS for the common base. Happen from time to time that you do it with the load as well. And the rarely used one is that Z out should be much smaller than the load for maximum voltage transfer. Okay, so just a side note, since the bias transistors has no influence on input impedances or any of that, if there's a voltage divider bias, you can just go straight ahead and apply the rule of thumb. If it's a single resistor in a dual rail, you can use a maximum base resistance required. You can use any resistance below that one. Um, it doesn't really matter as long as the bias is stable. So the input impedance is quite dependent on the bias. Right, so again with this figure, when to use VCC over 2 and VCC over 3. With the dual rail, draw yourself a line. This is for bias and use VEE, and we use VCC over 2 for those two. And when we have the split like this, the natural thing to do is to select all three of those the same, except in the case where a larger gain or increased RC is required, or a larger output swing is required. Just note that this decreases our stabilization. But the VCE equals to IC not equal to VE is a more common case when we are using R load prime. Okay, so don't go directly ahead and assume VCC over 3 when you're dealing with R load prime. It can happen that with increased RC value, that these two voltages will increase and VE will be a smaller value. It could also happen that VE is a larger value, not necessarily smaller. Okay, so be careful of that, and we are also going to use this in one of the examples today. So to demonstrate R load prime a bit better. Okay, the common base summary. The small signal model, I left out R out of the transistor. So we assume this to be infinite just to make our life easier when designing. The input impedance is all the resistances seen at the emitter parallel to R pi over beta R plus 1, or just RE parallel to small re. And typically the bias resistor will be much larger than small re, and it will work out that your input impedance is 1 over the transconductance. And down here we have exactly the same thing going on as the common emitter amplifier, just it is not inverted at the output. Right, again the loading effects. So our GV, our maximum power transfer, and yeah, these are quite standard with all the amplifiers. So, and it's been done a lot in all the other videos. So this is just more a small reminder. So let's do some examples. So let's say we have a common base amplifier loaded with a 22 kilo ohm resistor, a VCC of 24 volts. Sometimes in transmitters or receivers, it will have very large VCC value. This is to help accommodate for a very, very large gain and a very large output swing. They even increase the rails to accommodate larger collector resistors just to have bigger gains. Okay, so with this one, our specification is that we need to design for a 200 volts per volts AV, so this is loaded gain, with our R load prime equal to 10 kilo ohm. So this is the combination of our collector and our load resistor right here. And we need to find all the components and calculate all the parameters, assuming that there is a source resistance of 50 ohms right here. Now this problem says nothing about the swing, it says nothing about the input impedance. We are mainly focused on the gain here. So in this problem, Zn is Re R pi over beta plus 1, AV0 is GMRC, AV is GMR load prime. It's not stated here, but that's the other one. And for this problem, I went ahead and said that we're going to use VCE's ICRC is equal to VCC minus VE over 2. This can still work out to VCC over 3 if VE is equal to one of these two parameters here on the side. So this one is even applicable for VCC over 3 case. But typically with R load prime approach, we are going to have a different VE value. Okay, so VE's value, VB's value, VB is a voltage divider, and the rule of thumb. So these are all the equations or adaptations that we are going to use in this problem. So for our solution, AV is 200 volts per volt, R load prime is 10 kilo ohms, and we know that our loaded gain is GM R load prime. From that we can calculate our transconductance, and if we multiply this with 25 millivolts, we convert it to our collector current as 500 microamperes. Then we can take our R load prime and we can figure out what our RC is by reversing this process. So we get our output impedance RC as 18.33 kilo ohms, and the standard E12 value there is 18 kilo ohms. Right, if we multiply the 18 kilo ohms with 500 microamperes, we get our VCE Q point and our IC RC value equals to 9 volts. So this is 9 and this is 9. 24 minus 18 is what? 6 volts. Okay, so we plug in it into this equation, we will also get 6 volts, and that is our emitter voltage, and we can get our emitter resistance as 12 kilo ohms. Okay, so there's our first two resistors designed. Now for the biasing resistors, we know our base voltage is going to be 6.7 volts, so 6 plus 0.7 is a voltage divider of 24 over our two resistors. Using the rule of thumb, we get 50 microamperes. 24 divided by 50 is 480 kilo ohms. So the combination of these two resistors should be 480 Ks. If we simultaneously solve these equations, we get RB2 as 154 Ks and RB1 as 346. Let's choose that 150 and that 300 kilo ohms, and there is our biasing resistors done. Okay, now on to the admin. If we assume RE is much greater than small re, and we can see 12 kilo ohms is pretty much a very large value, and that will easily be greater than our RE over here. And if we assume beta is very large, our input impedance tend to be 1 over the transconductance, and that is about 50 ohms for this problem. So there we have our output impedance and our input impedance. Let's quickly recalculate all the gains and see what we get. So if we take AV0 is GMRC, we get 360 volts per volt, it's 51.1 decibels. Then I recalculated the loaded gain to 9.9 kilo ohms, and this is then just 198 volts per volt or 45.9 dBs. Zin being equals to Rs, this will be multiplied by a half, and that gives us 99 volts per volt or 39.9 dBs, technically something close to 40 decibels right here. So let's go over to our simulation and verify our results. So here is our simulation setup. So if we quickly cut off the input and run it, we can find our DC points. So this is 550 microampere, so that's very close to the 500 that we actually want. That's node 3, this is node 1. Let's quickly subtract these two. And that gives us 7.55 volts. That is a bit different from the 9 that we actually want. There's a bit more over this resistor here, and that is due to the choice of RB2. I think RB2 might be better at 120 kilo ohms in the end of the day, but this is not a big crisis. Let's run the simulation with our input, and that gives us a very nice swing, 1 plus minus 1 volt from 10 millivolts, and that is a gain of 100 roughly. So looking at our inputs, this is 5 millivolts, that is 10 millivolts. Our input impedance is about 50 ohms, just like our RS. And let's run the transient and see what the transient, no, sorry, not the transient, the AC analysis, and see what the AC analysis brings us in terms of the gains that we want. So this is the total gain at 39.969 dB, so close to 40. Let's make this a very small value, taking our input loading out of the equation. And that gives us 36.1 decibels. That's close to 45.9. It's a bit higher. Doesn't matter. And $50.97. That's very close to 51 decibels for the maximum gain. So I would say we achieved all our goals for this amplifier. Let's do another example. The second example here says that we're again going to load it with 22 kilo ohms, but this time it's a dual rail application, plus minus 15 volts. It says maximum power transfer from the source is required. Assume that we have a source of 100 ohms. design for maximum swing, and calculate E12 values, find all the necessary parameters afterwards. Right. So not much has changed on the small signal side. On the DC bias side, we are using VCE is ICQ RC VCC over 2, and the emitter is going to be responsible for our bias, and then just the the maximum value for RB and how to calculate it. Right. So let's assume that our emitter resistor is going to be much larger than small re, so we can say that the source is equal to input impedance is 1 over the transconductance is 100 ohms. Reworking this will give us a transconductance of 10 milliamperes per volt, and if you multiply that with 25 milli, it will give us 250 microamps. Okay, since we want maximum swing in this one and we don't have any R load prime requirements or specific gains that we're designing for here, we can use the VCC over 2 here. Well, we can't use it over 3 because it is a dual rail, so that is purely responsible for the bias in any case. So that yields 7.5 volts. Z out RC becomes 50 kilo ohms, and I chose it as 27 kilo ohms. Could have gone with 53 as well. That will boost your gain just a little bit. Doesn't matter in the end. It's all up to you when you're actually designing something. For a test or something, I would be happy with this. If I need to put a reason why I go with 27, that is closer to the 22 kilo ohms that we have as our load, and that will actually promote maximum transfer to the load a little bit better than a 33 kilo ohms. So that would be my reasoning for choosing the smaller value. Then using V over RE is our ICQ point with the necessary assumptions, and that yields 60 kilo ohms for our emitter resistor, choosing 56 kilo ohms as the E12. Then RB should be smaller than VBE over IB, or beta VBE over IC. That's 560 kilo ohms. There is a value like that. We just pick it the same. Anything less will be acceptable because this is just a bias or a path of a current into the base of the amplifier. Okay, doing checks. GMRC is 270 volts, 48.63 decibels. Calculating R load prime, you can also do this with a voltage divider method. It will be exactly the same. This is just for good practice. Gives 12.12 kilo ohms. That's a gain of 121 volts per volt, 41.67 decibels. And then we have matching, so this divided by 2 is 60.6 volts per volt, and that is 35.65 decibels. Let's go over to the simulation and check our results. So here is our simulation set up. Let's delete this path right here and check out DC. That is almost 250 microamperes on the dot. And that's V1, that's V3. Let's quickly subtract the two. That is much higher than what we calculated. Yeah, they should be closer to 7.5, but our swing will in any case never reach those values, so no matter. It is design equations and they're supposed to just kind of guide you in getting an amplifier going. I'm sure if we decrease this by a lot, let's go for 70, things might be better. -8.3 -1. Oh, yeah, but that's because we're working from zero. The voltage at this point is increasing it. My bad. I forgot about negative voltage sitting right here. So yeah, our VCE will be a tad larger, but even with that 470 being a smaller value, our bias is still very close to 250 microamps. Okay, so running this, we see we have a nice output. Quickly check the input. That's 5 milli, that's 10 milli. We have input impedance of 100 ohms. That is working out fine. Let's check our gains. Boat plot. And with all the loading effects, 35.2, we have 35.6. It's fairly close. Let's remove our input, make this very small. It's 40.9, 41-ish. It's close enough. Make this 22 meg. And that is 47.6, 48.6, what it should be. That is on its way to 48. The reason why these values are typically a bit off is we do not include the effect of R out of a transistor in our calculations. You can do that if you want to be more accurate, but this is, to be honest, close enough. So yeah, and that's our circuit verified. So that is a video on common base amplifier design. It's actually not really difficult to design as an amplifier. Thank you for watching and see you in a next video.